Hello everyone. So today we're talking about chapter 3, which is part 1, looking at measures of energy. As noted in chapter 1, the body uses the food we eat to provide energy, to build and repair tissue, and to regulate metabolism. Of these 3 functions, the human body ranks energy production first and will use food for this purpose at the expense of the other 2 functions in time of need. Energy is the essence of life. Through technological processes, humans have harnessed a variety of energy sources such as wind, waterfall, the sun, wood, and oil to operate the machines invented to make life easier. However, humans cannot use any of these energy sources for their own metabolism, but must rely on food sources found in nature. The food we eat must be converted into energy forms that the body can use. Thus, the human body is equipped with a number of metabolic systems to produce and regulate energy for its diverse needs, such as synthesis of tissues, movement of substances between tissues, and muscular contraction. The underlying basis for the control of movement in all sports is human energy, and successful performance depends upon the ability of the athlete to produce the right amount of energy and to control its application to the specific demands of the sport. Sports differ in their energy demands. In some events, such as the 100-meter dash, success is dependent primarily on the ability to produce energy very rapidly. In others, such as the 26.2-mile marathon, energy need not be produced so rapidly, but must be sustained at an optimal rate for a much longer period. In still other sports, such as golf, the athlete need not produce energy at varying rates, comparing the drive with the putt, but must carefully control the application of that energy. Thus, each sport imposes specific energy demands upon the athlete. Sports scientists have coined the term sportomics to evaluate the metabolic response of the athlete under varying conditions, such as weather changes. A discussion of the whole role of nutrition as a means to help provide and control human energy is important from several standpoints. First, an inadequate supply of necessary energy nutrients as a source of fuel, such as muscle glycogen or blood glucose, may cause fatigue. Fatigue also may be caused by the inability of the energy systems to function optimally because of a deficiency of other nutrients, such as selected vitamins and minerals. In addition, the human body is capable of storing energy reserves in a variety of body forms, including body fat and muscle tissue. Excess body weight in the form of fat or decreased body weight due to losses of muscle tissue may adversely affect some types of athletic performance. Energy exists in a form of other forms in nature, such as the light energy of the sun, nuclear energy and uranium, electrical energy and lightning storms, heat energy and fires, and chemical energy and oil. The 6 forms of energy, mechanical, chemical, heat, electrical, light, and nuclear, are interchangeable according to various laws of thermodynamics. We take advantage of these laws every day. One such example is the use of the chemical energy in the gasoline to produce mechanical energy, the movement of our cars. In the human body, 4 of these types of energy are important. Our bodies possess stores of chemical energy that can be used to produce electrical energy for creation of electrical nerve impulses, to produce heat energy to help keep our body temperature at 37 degrees Celsius or 98.6 degrees Fahrenheit, even on cold days, and produce mechanical energy through muscle shortening so that we may move about. For earthlings, the sun is the ultimate source of energy. Solar energy is harnessed by plants through photosynthesis to produce either plant carbohydrates, fats, or proteins. They are all forms of stored chemical energy. When humans consume plant and animal foods, the carbohydrates, fat, and proteins undergo a series of metabolic changes and are utilized to develop body structure, to regulate body processes, or to provide a storage form of chemical energy. In the human body, 4 of these types of energy are important. Our bodies possess stores of chemical energy that can be used to produce electrical energy for creation of electrical nerve impulses, to produce heat energy to keep our body temperature at 98.6 degrees Fahrenheit, and to produce mechanical energy through muscle shortening so that we may move about. So what terms are used to quantify work and power during exercise? Energy has been defined as the ability to do work. According to the physicist's definition, work is simply the product of force times vertical distance, or in formula format, work equals force times distance. When we speak of how fast work is done, the term power is used. Power is simply work divided by time, or power equals work divided by time. Two major measurement systems have been used in the past to express energy in terms of either work or power. The metric system has been in use by most of the world, while England and its colonies and the United States have used the English system. In an attempt to provide some uniformity in measurement systems around the world, the International Unit System, or SI, has been developed. Most of the world has adopted the SI, which is comparable to the metric system. Although legislation has been passed by Congress to convert the United States into the SI, and terms such as gram, kilogram, milliliter, liter, and kilometer are becoming more prevalent. It appears that it will take some time before this system becomes part of our everyday language. The SI is used in most scientific journals today, but the other two systems appear in older journals. Terms that are used in each system are presented in Table 3.1. For our purposes in this text, we shall use several English terms that are still in common usage in the United States, but if you read scientific literature, you should be able to convert values among the various systems if necessary. For example, work may be expressed as either foot-pounds, kilogram, meters, joules, or watts. For example, if you weigh 150 pounds and climb a 20-foot flight of stairs in 1 minute, you have done 3,000 foot-pounds of work, which may be converted to the metric system and international system. 1 kilogram is equal to 7.23 foot-pounds. So you would do about 415 kilogram. And in other terms, 3,000 foot-pounds divided by 7.23 foot-pounds equals 415 kilograms. 1 joule is equal to about 0.102 kilograms. So you have done about 4,062 joules of work. 1 watt is equal to 1 joule per second. So you have generated about 68 watts of power. Some basic interrelationships among the measurement systems are noted in Table 3.2. Other equivalents may be found in Appendix A. So how do we measure physical activity and energy expenditure? For research purposes, exercise and nutrition scientists are interested in measuring work output and energy expenditure under two conditions. One condition involves specific output and energy expenditure under two conditions. One condition involves specific techniques in controlled laboratory research, whereas the other condition involves normal daily activities, including actual sports performance. Other than researchers, many physically active individuals, for various reasons such as body weight control, want to know how much exercise they have done and how much energy they have expended. Over the years, numerous techniques have been used to quantify physical activity and energy expenditure. Given the worldwide increase in obesity and related diseases such as diabetes, quantifying physical activity is very important, not only for medical scientists, but also for the typical individual who exercises for its manifold health benefits. Recent research and reviews, such as those by Bort-Brioude, Consumer Reports, and Soda and Chen, as well as Hills, Hongu, Li, Liu, Montoy, and Scholler, and other colleagues, have documented various methods used and provided an analysis of their accuracy and usefulness, and they serve as the basis for the following discussion. Hills and others indicate that it is important to appreciate that physical activity and energy expenditure are different constructs. Physical activity involves bodily movement, which increases energy expenditure above resting levels. In many cases, objective measures of physical activity may be used to predict energy expenditure. All of the following techniques have been used to collect data on physical activity and energy expenditure specifically for research purposes, but may be useful for individuals interested in monitoring their personal exercise habits. A detailed discussion of such measurement techniques is beyond the scope of this text, but based on the research cited above, here are some highlights of the various methods. Physical activity questionnaires. The use of these questionnaires was one of the first methods to assess physical activity and is still widely used. Although some researchers note that physical activity questionnaires may have potential as a source of rich descriptive data, most contend the data obtained are subjective, not objective, in nature, and thus the validity of the data obtained is questionable. For example, Matthews and others noted that attempts to quantify physical activity energy expenditure via questionnaires are known to contain substantial errors. Heart rate monitoring. It's an easy, effective means to monitor exercise intensity in aerobic exercise. In and by itself, heart rate does not measure energy expenditure, but if calibrated with oxygen consumption in an exercise protocol, it may be used to assess energy expenditure in a given individual. The use of heart rate in planning an exercise program is presented in Chapter 11. When conducting research, exercise scientists need accurate measures of work output and energy expenditure. So an ergometer, such as a cycle or arm ergometer, is designed to provide accurate measurement of work, including measures of power and total work output over specific periods of time. For example, bicycle ergometers provide work output in joules and watts, measures of work and power respectively. However, ergometers do not evaluate energy expenditures such as calories expended. Exercise machines, particularly cardio machines such as treadmills, stationary cycling devices, elliptical trainers, and step machines, are examples of ergometers. Many commercial machines are configured to provide an estimate of exercise intensity, such as heart rate monitoring, as well as energy expenditure, such as calories expended. Some of these machines use computerized standard formulas to predict energy expenditure based on a typical individual, while others incorporate data input from the users such as gender, age, body weight, fitness level, and heart rate. In general, the more personal data the machine uses, the more accurate will be the prediction of energy expenditure. So if we look at measurements of energy expenditure, calorimetry is something that we tend to look at. Our bodies produce heat at all times, even at rest. When we exercise, heat production increases rapidly and in proportion to energy expenditure. Calorimetry is the measurement of heat production by the body. Figure 3.2 illustrates a bomb calorimeter, which may be used to measure the energy content of a given substance. For example, a gram of fat contains a certain amount of chemical energy. When placed in the calorimeter and oxidized completely, the heat it gives off can be recorded. We then know the heat energy of 1 gram of fat and can equate it to various units of energy. Direct and indirect calorimetry are two methods of measure energy expenditure in humans. Pictured here is a bomb calorimeter. The food in the calorimeter is combusted via electrical ignition. The heat given off by the food raises the temperature of the water, thereby providing data about the caloric content of specific foodstuffs. Direct calorimetry is a large, expensive whole-room calorimeter or metabolic chamber are available that can accommodate human beings, and a water cooler gradient layer can measure their heat production directly under normal home activities and some conditions of exercise. The limited size of such units may limit the type of physical activity, but they are equipped comparable to a hotel room for daily living activities. Other indirect calorimetry in such of a laboratory condition, this method determines the amount of oxygen consumed and carbon dioxide produced to calculate energy expenditure. The test may also be used to measure VO2 max and other measures of cardiovascular or respiratory function. Whole room calorimeters also use this method, but it may also be used in other laboratory conditions. Moreover, lightweight portable oxygen analyzers are also available to record energy expenditure in freely moving individuals, including those involved in some sport activities. In essence, oxygen is needed to metabolize carbohydrate, fat, and protein for energy production in the body. And if we can accurately measure the oxygen consumption and carbon dioxide production of an individual, we can get a pretty good measure of energy expenditure. Another technique is doubly labeled water technique. Scientists indicate that the DLW technique is the gold standard technique for measuring total daily energy expenditure in individuals in a free living environment. It is safe, non-invasive, and convenient for users over the course of a week or more. In brief, the subject ingests water with stable isotopes of hydrogen and oxygen, which emit no irradiation. Analysis of urine and blood samples provides data on hydrogen and oxygen excretion. The labeled oxygen is eliminated from the body as water and carbon dioxide, whereas the hydrogen is eliminated only as water, which may provide an estimate of carbon dioxide fluctuation that may be converted to activity, but they are they earn energy expenditure. Despite the advantages of this technique, it does not provide information on the type, intensity, or duration of physical activity, accounting for some of the total energy expenditure. So what is the most commonly used measure of energy? Although there are a number of different types of ways to express energy, the most common term used in the past and is still the most prevalent and understood in the United States by most people is calorie. A calorie is a measure of heat. 1 gram calorie represents the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. A kilocalorie is equal to 1,000 small calories. It is the amount of heat needed to raise 1 kilogram of water 1 degree Celsius. In human nutrition, because the gram calorie is so small, the kilocalorie is the main expression of energy. It is usually abbreviated as kcal, kc, or c, or capitalized as calorie. Throughout this book, calorie or C will refer to the kilocalorie. According to the principles underlying the first law of thermodynamics, energy may be equated from one form to another. Thus, the calorie, which represents thermal or heat energy, may be equated to other forms of energy. Relative to our discussion concerning physical work, such as exercise and its interrelationships with nutrition, it is important to equate the calorie with mechanical work and chemical energy stored in the body. As will be explained later, most stored chemical energy must undergo some form of oxidation in order to release its energy content as well. The following represents some equivalent energy values for the calorie in terms of mechanical work and oxygen utilization. Some examples illustrating several of the interrelationships will be used in later chapters. So 1 calorie is equal to 3,086 foot-pounds, or 1 calorie is equal to 427 kilograms. 1 calorie is equal to 4.2 kilojoules, or 4,200 joules. And 1 kilogram is equal to 2 milliliters of oxygen approximately. Although the calorie is the most commonly used expression in the United States for energy, work, and heat, the kilojoule is the proper term in the SI and is used by the rest of the world. It is important for you to be able to convert from calories into kilojoules and vice versa. To convert calories into kilojoules, multiply the number of calories by 4.2, 4.186 to be exact. To convert kilojoules into calories, divide the number of kilojoules by 4.2. Simply multiplying or dividing by 4 for each respective conversion will provide a ballpark estimate. In some cases, megajoules or millijoules are used to express energy. 1 millijoule equals about 240 calories, or 4.2 millijoules is the equivalent of about 1,000 calories. Through the use of a calorimeter, the energy contents of the basic nutrients have been determined. Energy may be derived from the 3 major foodstuffs: carbohydrate, fat, and protein, plus alcohol. The caloric value of each of these 3 nutrients may vary somewhat depending on the particular structure of the different forms. For example, carbohydrate may exist in several forms, such as glucose, sucrose, or starch, and the caloric value of each will differ slightly. In general, 1 gram of each of the 3 nutrients and alcohol measured in a calorimeter yields the following calories. 1 gram of carbohydrate is equal to 4.3 calories. 1 gram of fat is equal to 9.45 calories. 1 gram of protein, 5.65 calories. And 1 gram of alcohol, about 7. Unfortunately, or fortunately, if one is trying to lose weight, humans do not extract all of this energy from the food they eat. The human body is not as efficient as the calorimeter. For one, the body cannot completely absorb all the food eaten. Only about 97% of ingested carbohydrate, 95% of fat, and 92% of protein are absorbed. In addition, a great percentage of the protein is not completely oxidized in the body. with some of the nitrogen waste products being excreted in the urine. In summary, then, the caloric value of food is reduced somewhat in relation to the values given previously. Although the following values are not exactly precise, they are approximate enough to be used in determining the caloric value of the foods we eat. Thus, the following caloric values are used throughout this text as a practical guide and what we'll be using primarily in this course. So 1 gram of carbohydrate is equal to 4 calories. 1 gram of fat is equal to 9 calories. 1 gram of protein is equal to 4, and 1 gram of alcohol equals 7 calories. So for our purposes, the calories in food represent a form of potential energy to be used by our bodies to produce heat and work. However, the fact that the fat has about twice the amount of energy per gram as carbohydrate does not mean that it is a better energy source for the active individual. We'll see that later in later chapters when we talk of the efficient utilization of body fuels. All right, so that concludes our talk today on looking at human energy sources. We'll be going into that a little bit more in the second part of it. I look forward to talking to you soon. Thanks. Have a good day.